going to be talking about section 14.5, and our main topics are going to be gradients and directional derivatives. This is actually one of my favorite sections. I think it's time to get together a lot of really interesting visual representations, and this is where vector calculus is cool. Our learning goals for today are to compute gradients and represent gradients graphically using vector fields. We also need to get into a little bit of theory to understand what goes on when we take directional derivatives. So to get to that point, we're going to talk about compositions of paths with two variable functions. We're also going to compute chain rule for paths, and we're going to use these as tools to be able to compute directional derivatives. And then we're going to end today with a couple of really cool applications. So we're going to talk about geometric interpretations of gradients using contour plots. And we're also going to use gradients to find normal vectors to level surfaces. This is our #1 tool for being able to find normal vectors to surfaces are helpful because that helps us to find tangent planes for surfaces other than two variable functions. So to start off, we're going to jump right in by just defining what a gradient is. A gradient, written as an upside down triangle f. If we have a two variable function, this is going to be the partial derivative of f with respect to x. Ooh. This is a very important error that I almost made. And then the partial derivative with respect to y in the second component. Notice that my inputs are going to be points in R2, whereas my output is a vector. Gradients have outputs that are vectors. This is an important part of vector calculus. This gradient symbol, I will read this as the gradient of f is given by. The symbol itself is actually called a del symbol. Perhaps that's something that you've run into in a physics class or any type of applied science class. We can also take gradients of functions that have more than two variables. So here's a three variable function, and my gradient is exactly what you might expect. It's the partial with respect to x in the x component, the partial with respect to y in the y component, and the partial with respect to z in the z component. Again, my inputs here are in R3, they're points, and my outputs are vectors that have three components, three-dimensional vectors. So let's look at an example of calculating a gradient. If I have a two-variable function given by f of xy is equal to x squared minus y squared, then I can compute the gradient. My gradient of f of xy is just going to be the partial derivative with respect to x, which in this case is really easy, 2x in the x component of the vector, and then the partial derivative with respect to y in the y component of the vector, which in this case is negative 2y. The cool thing is the way that we go about representing this. So when I decide to represent this, I can represent this as what we call a vector field. My inputs are xy coordinates, so I'm just going to graph this on the xy plane. And I'm going to have my input point be the base point of a vector. So for example, if my input is 0, 0, I'll write these as xy. Xy values are my inputs, and my outputs are my partials with respect to x, and my partial with respect to y, which is a vector. So my input is the point 0, 0. My output is just the vector 0, 0. That's sort of a boring example. I can't really draw what a vector that's a 0, 0 vector looks like. But if I were to have an input of the point 1, 1, it means that my output is going to be a vector given by 2, negative 2. And the way that I would plot this on my vector field, I'll even label it as a vector field. I'm going to plot it by having the base of my vector start at the point 1, 1. This was my input value into the function. And then the output value is going to be a vector emanating from 1, 1 that goes 2 in the x direction and negative 2 in the y direction. So it's a vector that looks like this. And then as I plot different points, let's say I plot the point 1, 2, my output is a vector given by 2, negative 4. So as I go over 1 and up 2, my vector is now going to be twice as steep, pointing 2 in the x direction, but negative 4 in the y direction. It's going to go all the way down like this. And I can continue plotting vector field arrows that would look like this. To fill in the entire vector field would take a lot of work, and we'll look at what that looks like using technology, but I'm going to plot just a couple of other points to give us an idea. So if I plug in the point negative 1, 1, my output is going to be the vector negative 2, negative 2, which means that if my base point is at the point negative 1, 1, my vector in this case is going to be going negative 2 in the x direction and negative 2 in the y direction, which is down this way. And it turns out the subsequent vectors are going to go down more and more negative as I go that way. Next, I could try plugging in the point negative 1, negative 1, which now gives me the vector negative 2, positive 2. So starting at the point negative 1, negative 1, my vector is now pointing up this way. And finally, if I were to plot the point 1, negative 1, you would see that my output vector would be the vector 2, 2, which is pointing up this way. And this just looks like a mess of arrows as I write it on the board. If I were neat and organized about how these arrows were placed here, you could get an idea of the fact that, one, the motion of my vectors, they're pointing towards the x-axis. That is, regardless, if my y values are positive, the vectors are pointing downwards, and if my y values are negative, my vectors are pointing upwards. Another thing that is commonly done that you'll see on the graphing technology as well is that instead of writing the full length of the vector, because that gets really messy, you see that these vectors start intersecting, sometimes you normalize the vectors. So instead of writing the full length of them, you just write the unit length of the vectors. And that way you can get a sense of the direction of the way that the plots are going without actually having them overlap. And it makes a cleaner plot if you just look at the normalized vectors when doing these plots. Well, for our next topic, we're going to take a little detour, and before we can get to directional derivatives, we're going to talk about derivatives of paths. So first you need to know what a path is. A path is exactly like what we talked about as a vector-valued function, only our outputs, instead of being vectors, are going to be points. So essentially, I'm just parameterizing some curve in 3 space. That my input is a single t value. As t changes, it gives me either different points in R3 or different points in R2. So for example, one of my favorite paths in R2 is the path given by cosine of t, sine of t. And I might put the restriction on t that t is going to be between 0 and 2 pi. So this is exactly like the vector-valued functions where my outputs were vectors with each of these component functions, only this time, instead of thinking of them as vectors as outputs, I'm going to instead think of my outputs as just points in space. My initial point where t equals 0 is the point where my cosine of t is 0, which means that my x-coordinate is 1, and the sine of 0 is 0. So this is my initial point where t equals 0. When thinking about paths, this is where paths get interesting. You can compose paths with functions. So I'm going to compose this path, c of t, that we talked about right here, with the function that we talked about before when we were taking gradients. I'm going to look at the function f of xy being given by x squared minus y squared. So what does it mean to compose a path with a function? Really what I'm writing is I'm looking at f of c of t, meaning I'm plugging in c of t as an input into this function. And that makes sense because the output values in this case are both x's and y's. So algebraically, looking at this example, we see that my output is going to be f of the cosine of t, comma, sine of t. and I can evaluate this given this function x squared minus y squared, and I see that my functional outputs, I'm replacing my x coordinate with whatever the x component function is, which in this case I get cosine of t squared minus sine of t squared. So this is how I would algebraically represent a composition of this function with this path. That's the algebraic representation. What I think is more interesting is the geometric representation. So first, let's think for a second, what does this function x squared minus y squared look like? This is from one of our explorations in 14.1. This is a hyperbolic paraboloid. And we notice that when, let's just look at some of our traces. Our trace where y is equal to 0 gives us the parabola x squared equals z, meaning that I'm arcing up in the positive parabola direction along the plane y equals 0. However, when my x is equal to 0, the vertical trace where x equals 0 gives me a parabola pointing downwards. And remember that our level curves in this case were actually hyperbolas, that this looks like a saddle. And let's see if I can draw a saddle in three-dimensional space in a way that is meaningful for us. That it's curving up in the x-plane, and then it's curving down in the y-plane. So it's going to be something that looks, oh dear, I had a really great drawing on my paper earlier. Maybe I'll pause the video and come up with a good picture. Just a second. Hold your horses. Right? It's a saddle function. Hold your, never mind.